Okay, so aerodynamic damping, a powerful force for stability. So what is aerodynamic damping? Well, it's a moment on a teetering rotor that's proportional to the teeter velocity. In general, any wing also experiences damping of flatwise motion, but the important point is that it's a particularly strong effect on teetering rotors because it's neither elastic nor an individual blade motion. The whole rotor teeters as a rigid body with one blade moving forwards while the other is moving backwards. These equal and opposite motions change the velocity triangles of all the blade elements so as to give equal and opposite changes of their angles of attack, alpha. So the blade moving downwind has its alpha reduced, while the blade moving upwind has its alpha increased, and the resulting changes of lift oppose the teeter motion. Integrated across the rotor, this effect of lifting aerofoils, and it's most important that they are not stalled, makes this a powerful damper of the teeter motion. Thus, aerodynamic damping takes energy out of the teeter motion. So here's the second order differential equation for teetering. You've got a forcing moment for teetering that, and gamma is the abbreviation for teeter angle, subscripts dash and double dash, the derivatives with respect to time, J the inertia, Ca the aerodynamic damping coefficient, and K gamma the teeter stiffness, which with a simple teetering turbine, no pitch teeter coupling due to a delta 3 hinge or otherwise, means that centrifugal stiffness is the only significant stiffness term, so K gamma equals Kc. So why does aerodynamic damping matter so much? The centrifugally sprung mass terms don't determine the amplitude, and this comes from the fact that simple teetering is a resonant system, which Andrew and his co-authors originally derived in 1984, because the centrifugal stiffness is the inertia times the square of the rotational speed. And that's the frequency at which all aerodynamic forcing takes place. So the formula for natural frequency of simple teetering is the square root of the stiffness divided by the inertia. And so you get the result that the J terms cancel out and you end up with the natural frequency of teetering equals the rotational speed. So that means if it was undamped, the steady state amplitude would be theoretically infinite. In other words, damping completely determines the amplitude. And damping depends on the lift slope, dCLd alpha. That's the formula there. We've got air density, lift coefficient, angle of attack, and the blade geometry, basically radial distance, chord, and spanwise length coming into it. So the strength of aerodynamic damping can be estimated using two-dimensional value for dCLd alpha of 2 pi, and the following slide illustrates that. And even if you bear in mind that a real three-dimensional aerofoil has a lower lift slope between pi and 2 pi, which means that so long as you're on the lift slope, you are operating somewhere between the orange and the pink lines here with very, very low dynamic magnification. But if you lose damping altogether, if dCLd alpha integrated over the rotor equals 0, then in principle you've got infinite amplitude, and the turbine will bang itself to pieces if it does the stall regulation properly, I believe. Aerodynamic damping in terms of the three causes of bending. Well, if it's aerodynamic asymmetry, This effect definitely causes resonance because the forcing is periodic at once per revolution. And so the benefit of damping is the most important and obvious because it stops the teeter energy accumulating. And again, this graph illustrates that. With gyroscopic effect, it's not so much a periodic forcing. It's that the rotor wants to try and stay in its unyawed plane of rotation. But damping opposes this effect, as we'll go on to explain in a bit more detail. And of course, that's calculable using dynamic tools like bladed. Similar gyroscopic effects will occur due to platform motion on a floating turbine, but the angular velocities are significantly lower than those experienced by yaw regulation. So here's another result from that 1984 paper by Andrew and his co-authors, that the teeter amplitude is purely a function of the teeter forcing, the aerodynamic damping, and the rotational speed. So it's independent of rotor mass if it's a sinusoidal aerodynamic forcing, which applies for non-yawing cases. So that's been explained above in terms of the fundamentals of resonance. So the spring and mass terms do not determine the amplitude, and equation 5 tells us again that aerodynamic damping alone determines the teeter amplitude for a given aerodynamic forcing. Yawing is a little bit more complicated because the mass of the rotor does come into it. This time series illustrates that, for example, of an emergency shutdown in our simulations of the C16 and C112, you've got a period of fast yawing in both cases, different yaw rates, 10 degrees a second, 7 degrees a second. But both cases, the turbine's yawing about 90 degrees in a matter of a few seconds, which, if it were a perfect gyroscope, let's say, should lead to a teeter amplitude of 50 degrees, but it's the damping of the rotor stops it from staying in its original plane. So how does that work? So rather than unsteady aerodynamics forcing the teeter motion, yawing induces the teeters to start with because the shaft is yawing relative to the turbine rotor. And because of the teeter hinge, the turbine rotor's angular momentum is free to keep parallel to its starting axis of rotation, or relatively free, while the shaft is forced to yaw by its fore and aft bearings. So if it were a perfect gimbal arrangement, 50 degrees of yawing would result in plus or minus 50 degrees of teetering. So viewed from that perspective, equation 1 has no forcing moment which causes teetering. It's the yawing of the shaft induces relative teetering. So instead of equation 1, we need to ask the question, how much of that immediate yaw-induced teetering is needed to generate enough aerodynamic damping so the rotor will precess gyroscopically at the same speed as the shaft is yawing. This is the same effect as when gravity causes a spinning bicycle wheel to precess in the horizontal plane. And there's a couple of references here. An MIT professor gives a long explanation of it. I like this video of Dr. Tatiana from Texas A&M. The sound won't come through, but you'll be able to see it. So she's holding it without spinning and drops it, and it falls because gravity is making it fall. Not very interesting. What's more interesting, get it spinning and let it drop. And instead of falling, the gravity moment is making it precess. Just like the planet Earth, she says. Okay, going back to my presentation. So a formula can be for gyroscopic precession of the turbine can be derived considering the effect for what we've just seen with the bicycle wheel, where the rate of precession equals a torque in the vertical plane divided by the angular momentum. And in the case of precession of a bicycle wheel being axisymmetric like a disc, the torque applied is due to gravity, and you get that precession in the horizontal plane. Instead of gravity, in our case, it's the aerodynamic damping moment in the vertical plane, which causes a two-bladed teetering rotor to precess in the horizontal plane to follow the yawing of the nacelle. Equation 6 can't be directly used because the aerodynamic damping moment is not steady, it varies cyclically, and the two-bladed rotor is not axisymmetric. So Euler's equations need to be used. From equation 1, though, the aerodynamic damping moment is dA gamma dash, which provides a significant torque in the vertical plane because gamma dash is 90 degrees out of phase with gamma. Approximately simple harmonic motion will apply. And gamma is a maximum with the blades horizontal. So gamma dash is a maximum with blades vertical, and approximately equals omega x times gamma A. So therefore, the maximum value of the torque in the vertical plane is approximately Ca times omega x times gamma A. And because of the two cyclic variations that I mentioned before, it averages out at half that number as a torque in the vertical plane. So is that fast enough? To recap the last two slides, we're asking how much yaw-induced teetering is needed to generate enough aerodynamic damping so that the rotor will precess gyroscopically at the same speed as the shaft is yawing, thus avoiding further yaw-induced teetering. In other words, the initiation of yawing will cause the first swing of a teeter oscillation, and then a teeter velocity on subsequent swings, which will generate the aerodynamic damping. Typically, a maximum with the blades vertical, so you've got a damping moment in the vertical plane. And the answer is that yes, it is fast enough. Some further analysis using Euler's equations has to be used, and approximations for the values of the inertia and the different frames of reference. So to get a equation in the x, y, z coordinates, it comes out as the rate of precession is Ca gamma A over 2jx. And so you can estimate the amount of teeter excursion required to generate enough damping on subsequent swings so that the rate of precession is greater than or equal to the yaw rate of the nacelle. And rearranging with that criterion gives this formula for the required amplitude of that first swing. And then some further algebra with the Lock number gives a result that the first swing needs to be greater than or equal to 16 over times omega z over omega x, the yaw rate over the rotor speed, divided by the Lock number. And so when it's applied to the Seawind designs, it shows that continuous yawing would be equilibrated by aerodynamic damping caused by less than 4 degrees of free teetering. This compares to 11 degrees allowable, giving a large margin for simultaneous aerodynamic effects. So in summary, aerodynamic damping fully determines the teeter amplitude. In the non-yawing aerodynamic case, for fast yawing, a simplified analysis shows that the average damping moment is half of Ca omega x gamma A, which is sufficient to make the rotor precess with the yawing turbine, so the turbine stops increasing. Dynamic models can deterministically calculate that. This is shown here, where you've got some aerodynamic effects included on top of the yawing effect. And in the case of platform motion, you're also going to get some further effects, but these are much lower so the effects are small. And the teeter hinge will protect the tower and drivetrain from the turbine rotor-induced bending effects due to platform motion, whereas three-bladers don't have that protection and experience major tower load increases. Okay, so before I finish this section, I just want to address the question of stalling. One of the first questions I asked Silvestro a couple of years ago. You've got a fixed pitch turbine, why doesn't it stall? And as I say, I believe it's a bad combination leading to destructive undamped resonance. So does your regulation cause stalling? And the simple answer is no. The purpose of your regulation is to reduce the blade's average angle of attack, not increase it. And the figure below shows the average situation. So the first diagram is the case with no yaw angle, yaw misalignment 0. So you've got the wind straight on to the aerofoil and the familiar velocity triangle as shown. And when you yaw out of the wind, the main first order effect is that you are simply reducing the wind speed as seen by the rotor, so that wind vector is multiplied by the cosine of the yaw misalignment, just reducing the angle of attack. So this would be the case with blades horizontal in terms of the average case for the yawed turbine. This has been calculated through with a dynamic tool. Not sure if this is bladed or fast or CP lambda. In fact, there are a couple of different numerical models here, but this is for the Seawind 6, the radius of 63 meters of the maximum radius of the blades. So the blue and red lines show the result for the 25 meter station as a function of wind speed. So the turbine is yawing out of the wind as wind speed increases. And you can see that the angle of attack is well below 8 degrees. In fact, it reduces above rated. And the green and purple lines show the results for the 50 meter station. Can other effects cause stalling? Well, for any turbine, the inboard section can experience high angles of attack depending on twist, wind speed, and rotor speed. However, these aren't significant working sections, so have negligible effect on the overall aerodynamics. Your regulation introduces a couple of other considerations. So the vertical blades have advancing and retreating components, which add to or subtract from the R omega term. And this is arranged beneficially by always yawing the Seawind design anti-clockwise, viewed from above. So the resulting aerodynamic asymmetry opposes the effects of wind shear and tower shadow. I can show the resulting angles of attack on the following slides. Fast yawing does introduce another component which could affect the tangential velocity. However, it's still negligibly small compared to the steady tangential velocity. Even yaw rates of 10 degrees a second are small compared to rotor speeds of 10 or 20 RPM, which is 60 to 120 degrees a second. So this is the advancing, retreating blade effect on angle of attack at a range of blade stations. So this is for a wind speed of 20 meters a second, and the blue line shows the lift curve. So it's very clear where the stall point is. The diamonds show the operating range for minimum and maximum lift coefficient. So that will be the maximum will be the blade vertical retreating, and the minimum will be the blade vertical advancing of the top blade and the bottom blade respectively. And you can see the figures for the other four stations, 55 meters, 45 and 33 meters. So we're not getting close to stalling. This is the same thing for 24 meters a second, higher wind speed. So you can see a similar picture, getting close to stalling at the 33 meter station, but you're still operating up and down the lift curve. And importantly, as you can appreciate, because the turbine's rotating, if it does get into the stall region, it's going to be a dynamic stall, because a moment later it's come out of that position and having its angle of attack reducing. The inboard section, and these are the same wind speeds, 20 and 24 meters a second for the 13-meter station. So that does show going above stall, but this is less than 20% of the radius of the blades, and the aerofoils are actually tailored here to have a soft lift and drag coefficient. So we don't see any issue there. The simple point being that whole rotor stalling will not occur. It'll be negligibly small and transient. So your regulation gives the benefit of fixed pitch blades without the whole rotor steady stalling that is inherent with stall regulation. Teeter stability during startup and shutdown is easier to manage actually than for a pitch regulated teetering two-blader, which is a bit of an aside, but based on my experience with the wind flow turbine, that's my sense of it. So that's the end of section 2. Are there any questions about section 2? Roger.
Well, a few comments rather than questions. You use the term first swing, which I think might be sort of helpful for producing a mental model, but I don't think there's anything actually in the analysis that distinguishes the first rotation from the next. I mean, as soon as the blade gets away from horizontal, it's going to start precessing, and it'll do so until it gets near to horizontal the other direction. Obviously, when it is horizontal, you don't get any effect because second order effects take over for a short part of the range. Another comment on just the way you put things, which is, you know, one way of thinking of things, but some people might think of things in a different way. So when you talk about taking energy out of teeter, some people might think, well, we've just got a spinning disc here. The total kinetic energy isn't going to change, and that's true. So it's just the part that is accounted for in the teeter degree of freedom that is being reduced, which of course is what you want if you want to avoid getting near the teeter stops. But I
did say it's taking energy out of the teeter motion. Yeah. Very mindful of the previous discussion you and I have had. Yeah. Because I had the notion that the energy goes into the airstream, whereas you're of the view that it is conserved in the rotor and goes into useful torque driving the turbine, which I'm sure you're right, and is a good thing, I'm sure.
That's part of it, yeah. Yes, and the total kinetic energy is going to be the same if it's a soft drive. And then there's the other little point, which is the slide showing the effect of the lift slope on the dynamic magnifier. The point I'd want to make there is that what really matters is the dynamic magnifier multiplied by the equilibrium amplitude, because that is the thing that actually is the amplitude of theta that you get. So, for example, your slide shows a typical blade, but if you had a blade with twice the blade density, you'd get twice the dynamic magnifier, but you'd get half the equilibrium amplitudes. So the important thing at the end of that is actually equation 5, which doesn't distinguish the dynamic magnifier and the equilibrium amplitude, but only considers the product of them. So those are the 3 points where I was just wanting to say that you can describe the same thing in different ways, and it all comes to the same thing, but according to people's preferred mental models, different wording might be more helpful.
Thanks, Roger. Andrew.
I'm still grappling with the idea that the thing never stalls, and I thought that graph of the maximum minimum angles of attack was very interesting, and so that's making me understand a bit more how that could be the case. But I remember when we were doing, in the very early days, doing teeter analysis, and the big problem was starting and stopping, where most of the calculations, I think, do fall apart naturally. and you're saying that again, you're not expecting teeter impact or large teeter excursions, even when you're starting and stopping, or particularly when you're stopping, perhaps, where the blade will stall. I mean, because at low wind speeds, it will certainly stall. So, are you suggesting that it stalls, but it doesn't have any substantial excursions? That I do find difficult. So, I would have expected you to have to deal with teeter stop impacts, either in starting or stopping or both. So could you elaborate a bit on that? Because I'm still a bit puzzled by that.
Sure, and because I've thought about that too a lot, and certainly I agree that the wind flow experience with starting and stopping was you have to be careful how you start up and shut down because it's full span variable pitch. So you're going from 0 degrees pitch to 90 during the shutdown. And it's very tempting with full span variable pitch to just use the blade pitching to slow the machine down quite quickly. But to do that, you're feathering the blades so fast that you get negative torque on the rotor, aerodynamic torque on the rotor. And we realized that wind flow, that was a very bad thing in some wind conditions, high turbulence, or if you were off the wind 20 or 30 degrees due to a sudden wind shift or whatever. So we developed software in the aftermath of the 2005 event to manage that very, very carefully. So I have been thinking about, well, what will happen with the fixed pitch machine? And certainly I'm comforted by what happened in that 2005 event when it slowed from 48 to 40 RPM with fine pitch, which would be analogous to the C1 machine, and the teeter stability was very good. Just thinking about it more, and that diagram I showed where the angle of attack is fundamentally reducing, I thought to myself, well, are you even going to get negative aerodynamic torque on the rotor in the sense of, or negative lift on the blades? And you're not. I don't believe it's kind of fundamental that because it's fixed pitch. So you can imagine if you just yaw out of the wind, the momentum of the blades will keep them going for quite a while. It'll take a while to slow down because you've just got whatever drag there is on the blades, the friction, torsional friction coming from the drivetrain is slowing things down. And so it is a totally different type of shutdown from a variable pitch machine to just yaw out of the wind. And so the C-wind algorithm does involve some braking, some low torque braking to speed up the process once you yaw out of the wind, get the rotor basically shut down, then release the brake, let it mill over slowly until it gets the horizontal position and park. So yeah, I think it is, having thought through as best as I can, I don't think you're going to get teeter instability. You're not going to get the blades stalling, nor are you going to get negative lift on the blades, which we found at Windflow was almost as bad as stalling for teeter stability.
If you're operating at high wind speed, therefore at a high yaw angle, and then you lose the load, well, where do you go? I mean,
to 90 degrees.
You go to 90, do you?
Yes.
And you're saying going to 90. Well, I don't believe you can do the calculation, but you're saying, yeah, unless you have some measurements to show or some better calculations, I can't see how you could avoid at some point having a stall if we were operating at 90 degrees. But maybe I haven't thought about it carefully enough.
I don't
Yeah.
believe so. I welcome comments from Sesta or Sylvester on this point, but I think in principle, if you were in high winds and let's say you got up to maximum overspeed and then you're out of the wind to shut down, I can imagine without putting the brake on, the turbine will keep going for quite a while at 90 degrees, but it will gradually slow down due to a bit of aerodynamic drag and the friction in the system. And of course, putting the brake on with low torque will accelerate that process.
There's one other general question, which maybe we'll come to, but you are convinced you can yaw fast enough to deal with an emergency shutdown?
Well, yes, that's what we've modelled. I mean, the only thing I would add is that thinking about all these things over the last couple of years and not being able to shoot the idea down. And actually, Dave Quarton will remember how I tried to shoot the idea of two-bladed teetering down in 1987. I was very, very skeptical about it back then. But having thought about it, I started thinking about the wind flow turbine and what we would save if we got rid of the pitch mechanism, the bearings, the pitch rod, the pitch mechanism in the hub, the hydraulic actuator, all the control gear. So yeah, I'm quite keen to try this out with the wind flow design, which might be a little bit less scary than doing it with a 6 megawatt machine first up. David? Dave?
Yeah, okay. Just two points really. Actually, the first is more of a bit of a pedantic question for Roger. I think his approach to deriving this this equation he has at the end of the section there, I think is really elegant. It's quite nice to see it done in the way in terms of the precession of the rotor disc. But I don't think it needs to be done that way. And I just wanted to check that Roger agrees with me now that if he took the basic Teeter equation that was presented right at the beginning in a coordinate frame that's locked to the rotor shaft, the gyroscopic loading does become a periodic forcing function which can be simply added into that equation. And then you find the Teeter rate that corresponds to that gyroscopic load. And it drops out to be the same as what you find, or what Roger's found with the precession analysis. So your section is all based on this precession analysis, and that's fine. It's very elegant. Whether it's the most straightforward way for someone to understand coming new to this, I'm not sure. But I was interested to see whether Roger agreed, because I know he spent a lot of time thinking about this.
Yes, like I said, I did try and do it that way, but I wasn't convinced. I didn't convince myself that I'd done it right. So I thought, well, let's do it Euler's way. Everybody knows that Euler was right. So I was more confident of getting the right answer that way. And they came to the same answer. So
Okay, good.
And must acknowledge Roger's role in that. And I did insist on trying to keep it in X, Y, Z coordinates because that helped me really visualize the effect on yawing, and that's why I found the bicycle wheel metaphor helpful.
Fine. Yeah, I'm completely happy with that approach, and I think it's very elegant. The second point was just going back to really what Andrew was talking about in terms of whether the blades can stall at high wind speeds. I just did a back of the envelope calculation for a wind speed close to cutout, let's say 25 meters per second. The yaw angle will be about 70 degrees, let's say. So that means that the in-plane velocity sine of 70 degrees is about 90, but 0.9. So you've got about 20 meters per second, plus or minus, as the blades go around in plane. So there's obviously quite a big change in the angle of attack going on there on a cyclic basis. But I just wonder whether that's sufficient to trip us into stall, particularly when you are on top of that turbulence. I wonder whether the angle of attack variations and the fact that they're happening once per cycle will cause this dynamic stall effect. I think Steve may be a better person to deal with this, because my specialty is certainly not aerodynamics, but that does worry me a little bit whether dynamic stall will play a role given the angle of attack variations going on. I don't know whether you've obviously thought this through, Jeff, because I know you touched on it in your presentation, and I think you seem pretty convinced that it's not going to be a problem. But it is surprising when you think about the numbers involved.
One of the graphs was for 24 meters a second, which is pretty much 25 or cut out wind speed, and the 33 meter station, you're getting close to the maximum lift coefficient and a maximum angle of attack around 17 degrees or something.
Right.
But that's at the 33 meter station. Outboard of that, and of course, we all know that the wind loads go with the square of radius, because the tip speed goes with radius, and the velocity and the loads go with the square of speed. So the working section of a blade really is the last 50%. So if you haven't got stall at 33 meters out of 63, I'm comfortable with that, especially thinking, correct me if I'm wrong, when I say dynamic stall, I think of the graph that shows the angle of attack increasing and the flow stays attached because it's dynamic, because a moment later the angle of attack reduces, and so the flow can actually stay attached. So in that case, you don't have stalling as such. You actually enhance lift.
But you can get an hysteresis loop, I think, can't you? I mean, this is where Steve, I think, may be able to.
Well, that's the point. It's going both ways, because the delay is the time it takes for the shed vortex to develop and to leave the trailing edge, and you've got to have the reverse process as you come round. So you're in a hysteresis loop, which is, and I can't think off the top of my head how to quickly assess how quickly you're going through that hysteresis loop as your blade is rotating, but you either need to show that the unsteady aerodynamics is a very limited effect, or you need to model it fully in order to see how it interacts with the rotation.
Yeah, I have to point out the irony here. My contention is that whole rotor stalling, which is what a stall regulated turbine is designed to do, and plenty of three-bladers in the 1980s and beyond, the bonus machines in the 1990s through the early 2000s, used stall regulation with fixed hub three-bladers perfectly fine, except for problems about emergency overspeed systems and so on.
And blades falling off.
Blades falling off as a result. But to combine that with teetering, I maintain is a total no-no. And I've been corrected this afternoon, or people have tried to say tone that down, Jeff. So I'm very sensitive to stalling, and I can't see the problem based on these numbers and thinking about as what I understand dynamic stall to be, that it's not actual stall, it's a transient.
I think what's going to happen here, the dynamic stall is going to help, but in both directions, going up and coming down, until the rotational speed gets low, when the time will be long enough to develop the vortex, leave, and then it'll stall. So that's why when you're slowing down is when you'll get this problem. But it's clear that the dynamic stall will be very helpful in keeping the the flow attached. But at some point, particularly towards the end, it will leave, and then I think it'll vibrate. But it seems not.
which is but when it's slowing down, that's as Silvestro said. We use the brake, a gentle braking, a low torque braking, to quickly pass through any such instabilities, or just, we all know that you get loss of teeter, what I call loss of teeter stability when a rotor slows down.
It's just, something just occurred to me as we were talking, which is, have you modelled or looked at sudden changes of wind direction? If you're using the yaw system to control it, if you suddenly find you aren't in the yaw condition that you thought you were, you could be in trouble, couldn't you? Which would, if there was a sudden change of wind direction, is exactly what would happen.
Yes, well, the fast yawing needs to be, I think of it this way, that the fast yawing, if it's up to 10 degrees a second, which is analogous to the sort of pitch rates that we had, you could, and so long as teeter stability was okay with the 10 degrees a second, then that's what's available to you to do speed control, compensating for variations in wind, including wind direction. The blade pitch systems have to deal with. But having thought about that, I think that the first 30 or 40 degrees of yawing away from the rated condition of yaw angle 0, there's going to be a slower response time. Anyway, long story short, the sort of speed excursions that we get in our modelling of the C16 machine are something like plus or minus 25% in a worst case. And my only concern there is that I don't think we're going to be able to use the torque limiting gearbox if that is the case. But with an inverter system, it can handle those sort of speed excursions.
You say it well. There is a point there, Jeff, and that is that 40%. I think in one of the cases, increase in speed will increase the generator voltage by a similar amount. So your inverter system's got to be able to cope with a very significant excursion, and that's that sort of headroom significantly more than is normally designed into a wind turbine. And so there is it's not
40% though, it's plus or minus 25% on
you sent me a plot. You sent me a plot that showed 40%. I'm just reading off that one plot. I don't know how.
For the C16, the worst case I've seen is running at about 20 RPM on the rotor, up to 25, down to 15.
Well, I've got 20.
And turbulent wind, so that's plus or minus 25%. I think of it as.
It's 28 on the one that I'm looking at, but
really, okay.
I'm slightly exaggerating it, but these are still sort of greater than the 10-15% that's used on most large turbines. Mm-hmm. But that is something that can be engineered, of course. So but the turbulence is the thing that really that also exercises me is that if you add turbulence and in particular wind direction changes caused by large meteorological structures, then those have all got to be run through the checks on the behavior of the system.
Okay. I see Sesto has his hand up. He can probably answer those questions.
Yeah, I wanted to add a couple of things. First of all, an answer specific about the angle of attack at high wind. And that's it. Let me see if I can show you. This is at 24 RPM, at 24 meters per second. and this is at 70% blade station. You can see that the angle of attack stays between 6 plus or minus 6, so it is quite in the linear region most of the time. Second thing, and of course this happens with the turbine yawed out from the wind at 60-65 degrees. Second thing is about the stopping of the turbine. We really apply the brake with a low braking power, torque, sorry. When we are near to the stop, let's say it is about 6 RPM, but that's due mainly to the fact that we are approaching one of the own frequencies of the system. So we want to go through as fast as possible. And yes, of course, if we go through that slowly, we stay at that frequency, we can excite the teeter. But going fast enough through that area, and consider that at the point the applied torque can be very low to stop the rotor faster, then we don't see any significant increase of the teeter above the nominal values in operating conditions.
May I say so?
Yeah, of course, yes.
Yes, thank you. And I would add that before using the brake, the yaw system remain active. I mean, controlling the direction of the rotor disc. This is very important to mention.
Well, I'll have a go at going through section 3 in double quick time then.